Okay, so the goal for today is to finish general normal distributions uh, and talk about sampling distributions in the central limit theorem. We'll bump the last part of chapter 6, testing for normality, to a supplemental video. So I'll post that on YouTube under our same playlist as usual, and I will so that'll be up shortly after the recording for today. So just keep an eye out for that bit as a supplement. Maybe I'll put that in bold. And then also the plan for today, if we get to it, depending on how long the rest of chapter 6 takes, we might start chapter 7, confidence intervals. So, and the quotes of the day for today, by the philosopher Hume. The first quote is, "A wise man always apportions his belief to the evidence." So I think that is maybe particularly applicable to statistics and some of the Bayesian analysis that we have kind of recently talked about. Um, and another interesting idea from Hume is sometimes called Hume's guillotine, or the is-ought problem. And that is that ought statements cannot be derived from is statements. Or in other words, we've kind of stated this in a slightly different way at the beginning of the course, where we said, well, things like mathematics and statistics and even things like maybe physics and chemistry can give us a lot of insight into how the world is, that this thing is true or seems to be true. But then kind of the next level up of wisdom is kind of how we ought to use that, right? What ought we do with that knowledge or that understanding? That is a separate problem. And we have to, be a little bit careful to kind of stay in our lane, to not think that just because we've answered a tough is question, that necessarily gives us an answer to a tough ought question, right? Just because we can do something doesn't necessarily mean we should do that thing. So two things to think about from philosopher David Hume. Okay, so going back to general normal distributions, or the normal distribution family. Remember, this was where we said that we have a normal distribution that is parameterized by mu and sigma, the mean and standard deviation of the distribution. And last time we worked quite a bit with a single member of this normal distribution family, because we wanted to look at all the different types of questions that could come up while keeping as many things held constant as possible. So we dealt with an application of IQs, which are typically normed to a distribution that is normal with a mean of 100 and a standard deviation of about 15. Here we're going to look at a different member of the normal distribution family, a different mean and standard deviation in this example. Okay, so let's take a look at this example, masses of quarters. So let's suppose that the masses of quarters are normally distributed with a mean of 5.67 grams and a standard deviation of 0.06 grams. And let's suppose that we're trying to build a coin receiving slot for a vending machine. And, one of the important things with such a slot is that it's able to determine whether the thing inserted is a valid coin or not. And let's just assume that it only accepts quarters, so it doesn't have to tell quarters apart from dimes or anything like that. But its goal is to figure out if the thing inserted is a valid quarter or not. And it might have a couple different tests for this. Maybe there's a size test, and maybe there's a couple other things, but it might also look at the mass of the thing that's inserted. So for true quarters, we would expect something around in the ballpark of 5.67 grams for when that's inserted. We would expect that's what its mass to be. That's what its mass would end up being. But again, we know that not all quarters are exactly 5.67 grams. There's a little bit of manufacturing tolerance, and surely over the years, maybe some of the older quarters, a little bit of metal has rubbed away. They're a little bit, they've lost a little bit of mass over time. So we decide, okay, well, we will say that a quarter passes the mass test if its mass turns out to be between 5.64 and 5.70 grams. So 0.03 grams on either side of the mean. And we would like to know what proportion of quarters will be rejected, and is this reasonable? Uh, the first one we can certainly answer. That's an is question. The second one, is it reasonable? That's kind of an ought question, like, are we rejecting too many quarters? Well, we have to consider the trade-offs there. So, first question we can answer with certainty. The second question, we'll talk about some of the trade-offs. Okay, so what do I have? Let's let X be the mass of a true quarter. And I know that X is normally distributed with a mean of 5.67 and a standard deviation of 0.06. And our machine rejects quarters with masses outside the range 5.64 to 5.7. So probability that we reject our quarter is, well, I guess that's the probability that X is less than 5.64 or bigger than 5.70. That's kind of an annoying event to work with. Let's use the complementary event. That's 1 minus the probability we do not reject the quarter, that we accept the quarter as valid, at least according to just this test. And we do not reject the quarter if it's in this interval, if its mass is in this interval. If X is between 5.64 and 5.7. So this is the probability I'm interested in. What is the probability that the mass of a quarter is between 5.64 and 5.7, or what's the probability that this normal distribution falls between 5.64 and 5.70? So let's come over here off to the side and calculate this probability. And will remember we have to plug it back in over here and do 1 minus to get the answer at the end. But let's figure out what is probability 5.64 less than X less than 5.70. Here, X is a normal distribution. I've forgotten my color scheme from last time, but X is a normal distribution with mean 5.67, standard deviation 0.06. So this inflection point will be up here at 5.73, and this down here at 5.61. That's where one standard deviation away from the mean is where we change concavity from curving up to curving down, or vice versa. And I want the area between 5.64 and 5.70, so that is this area. I know that the area within one standard deviation of the mean, so from 5.61 to 5.73, is about 68%. So this should be, say well under 50%. Shouldn't be a tiny area. It shouldn't be like, 2%, but it should be under 50%. I can be pretty confident of that. Now my challenge here, I have two challenges. My one challenge is that I have information about probabilities related to Z, the standard normal distribution with mean 0, standard deviation 1. I have a question in X with a different mean of standard deviation. And my other challenge is that I have an area that's between two values and not a left tail area, which is what my table gives me. So I need to fix both of these. I need to get a left tail area, or maybe sum or difference of left tail areas. And I need to convert it into a standard normal distribution. And I think I said last time that my preference is always to convert to a standard normal as soon as possible. We can use a lot of symmetry and things in the standard normal distribution just a lot more easily than in the general normal distribution. So let's convert to Z, mean 0, standard deviation 1. My X indices of interest are 5.64 and 5.70. I've tried to draw them in green so they stand out a little bit. So I need to find z-scores for both of those. So I take those values, subtract off the mean of 5.67, divide by the standard deviation, 0.06, and I see that they're just negative 1/2, negative 0.5, and positive 0.5. I need to get plus or minus 0.03 divided by 0.06. And since I'm kind of running out of, I guess I could use red. Can use red. Well, I got an extra 0 in there. Negative 0.5 and positive 0.5. So I've converted this to a question in Z. Probability that Z is between negative 0.5 and positive 0.5. So now I've solved one of my problems. I have a question in Z instead of an X. So I'm closer to being able to use my table. I need to now reframe this question in terms of left tail areas. And we've seen how to do that in the past as well. I can start by taking all of the area to the left of positive 0.5. And I am going a little slowly through this because I know that it was, 5 days or so ago that we last did this. And we had our, good old daylight saving time change. So I think even though you get a little more sleep, it like kind of throws people off. I go to sleep at all random times and wake up at random times just because my schedules are all, different. So it doesn't affect me as much as most people, I think. But anyway. So this includes the area that we want to keep that's between negative 0.5 and positive 0.5. But it also includes a bunch of area that we don't want. So we have to get rid of that area. So I subtract off. Subtract off the area to the left of negative 0.5. And let me erase this. That's kind of in the way. So this is probability Z is less than 0.5 minus probability Z is less than negative 0.5. Now I have two left tail areas related to Z, the standard normal, and now I can just look up on my table what the answers are. Well, what these two answers are, and then subtract them. Probability Z less than 0.5. So that is a positive Z-score. Area to the left of 0.50. That looks like 0.6915. And then I have to subtract off probability Z less than negative 0.5. That is a negative Z-score. That matches my picture. Area to the left of negative 0.5, it'll be in this row. And of course, the 0/100ths column is that first column there, that's 0.3085. And then I can do what? 0.6915 minus 0.3085. That gives me 0.383. Going all the way back over here. is 0.383 less than 50%? Yes, it is. It satisfies that check. And remember, I have to come all the way back over 0.383 isn't my answer. I have to do 1 minus 0.383 to get the so this 0.383 is the probability that we accept a true quarter on the basis of this test. And 1 minus that, we can come over here and do 1 minus, and if we do second negative sign, that just says answer. That brings up our previous answer. 1 minus 0.383 is 0.617. So on the basis of this test, we would reject about 61.7%, let's just call it 2/3 or so, of true quarters. I mean, if somebody wants to buy a soda for $1, if we're rejecting, say, roughly 2/3 of quarters, they'd have to have like $3 in quarters, and they'd be putting their quarters in, to get 4 of them to kind of on average take. And I think we're being a little too picky here. I think this is too tight of a range. We can't be rejecting, 60 or something percent of real quarters that are put in. Nobody's ever going to use the machine. They're going to think the machine is broken and move on. So is this reasonable? Probably not, right? It's not mathematically provable or something that this is not reasonable, but I think we can all kind of agree that a machine rejecting 2/3 of roughly of good currency that's probably not very good for business. That's probably not a machine anybody's going to use. What if we said, okay, I want to accept the middle 95% of masses? I'm going to leave this as an exercise. We've done a similar problem before, kind of in the Z world. So what I want to know is, given my X distribution that has a mean of 5.67, standard deviation of 0.06, I want to come up with a lower bound and an upper bound that are symmetric about the mean. And I want the area between them to be 95%. So this is my goal. I'll leave this as an exercise. Try to work through this problem. If you need a little bit of help, if we do get to confidence intervals today, actually our discussion of confidence intervals will really mirror this type of problem. So we'll see that, we can use a lot of the same math and confidence intervals to answer a problem like this. Or if we don't quite get to confidence intervals, you can work through this as an exercise and, see where we should set our tolerances so that we accept the middle 95% of masses of true quarters. Where should our lower and upper bound be? We can probably hazard a guess or a rough estimate. So a guess or a rough estimate, well, we know that for a normal distribution, our empirical normal rule says that 95% of the distribution is within 2 standard deviations of the mean. That's a symmetric interval. So maybe our guess or an estimate would be mean plus or minus 2 standard deviations, or 5.67 plus or minus 2 times 0.06. So when you get an answer, you can get a more precise answer by using the table maybe. But when you do get an answer, it should be in this ballpark, right? It should be it should be somewhere in the ballpark of 5.67 minus 0.12, 5.67 plus 0.12, or 5.55 to 5.79. right? So that gives you kind of a rough guess, the rough estimate that you can use to check your answer. Did you get an answer that's pretty close to this interval solving this problem? All right, any questions? All right, let's move on then to the next big topic is sampling distributions in the central limit theorem. So the central limit theorem is it's quite an important theorem. It's probably our one of the two most important theorems of our course. So there's the central limit theorem and the law of large numbers, and both um, have a lot to say about how we take these mathematical models that are nice theoretical models but don't themselves say anything about the real world, and then how we actually port that over to the real world and overlay that on real world data. So that's what we're looking at here. We're looking at the second of those theorems, the central limit theorem. And we're building up to it. We have to understand this idea of sampling distributions first. So let's take a look at an example here. Let's consider the average number of heads on, say, one flip of a coin, and then on 2 and 3 consecutive flips of a fair coin. So we'll start with the n equals 1 case. So we have one flip of a fair coin, and we'll let x bar be the average number of heads on one flip. Now, it seems it's a bit silly to say it this way because the average number of heads on one flip of a coin is just the number of heads on one flip of a coin. But we're going to be generalizing this to 2 and 3 flips of a coin, so we'll keep our notation consistent this way. So I have two possible outcomes. I can get heads or tails on my single flip. The number of heads is 1 or 0, and the average number of heads per flip is, of course, 1 or 0. These are equally likely outcomes. So 1 and 0 come up equally likely, or 50% chance each. So here's the kind of interesting thing. I actually see that x bar, the average, is itself a random variable. We've talked about this in the past before. This is a bit of a conceptual shift from maybe when we were thinking of the average or the mean in chapter 3. But just to kind of remember that idea, we think of kind of having this population. And I take a sample. So maybe I sample these people from the population. That gives me a data set. And this data set has a mean x bar. So that was our chapter 3 perspective as we started here. Here's our data set, compute x bar. X bar is deterministic. There's no randomness to it. If we all had the same data set given to us, we would all compute, hopefully, x bar in the same way and get the same answer. But the thing is that actually this process here that happens before we write down and start analyzing the data set, this actually has randomness in it. So in other words, if somebody else went to this population and took a sample of size whatever, the same size, chances are they would get a different sample. And from that different sample, chances are pretty good that they would get a different x bar. So upon repeated applications of the process, sampling from the population, gathering the data set, and then computing x bar, we get different outcomes of x bar. In other words, we get maybe an x bar 1 here and an x bar 2 there, and maybe a different sampling would give me an x bar 3, and so on. X bar is actually a random variable. Right. So this was a fundamental change in the way we think about x bar from chapter 3. Chapter 3, we kind of started here and proceeded forward. We only thought about, I have a data set in front of me, what's X bar for this data? But if we back up the process to the beginning and we think about this whole process, we see that actually X bar is random. It's a random variable. It's non-deterministic. And it's because of their random sampling from the population, right? Again, if we have a class of, say, 20 stat students and I hand you all the same data set for heights of people in Pittsburgh, and I say compute X bar, you should all get the same number. But if I told each of you, go out and randomly choose 20 people in Pittsburgh, measure their heights, write them down, compute X bar, and come in to class, the next class meeting and, tell me what X bar you got, chances are very good you would all have a different X bar. Hopefully they would be pretty close to one another, but they wouldn't be exactly the same because you would have taken different samples. So X bar is a random variable, and being a random variable, it, has, say, a distribution, a probability distribution of some sort. It actually has a mean as well. We might call this mean mu X bar, mu subscript X bar, or the expected value of X bar, something like that. And X bar has, for instance, a standard deviation or a variance, sigma X bar. Sometimes we call this the standard error or the standard error in the mean. So this is a conceptual shift. X bar is a random variable because the sample that it's based on, the data set that it's based on, is the result of random sampling from the population. X bar being a random variable means that X bar itself has a distribution, it has a mean, it has a standard deviation, it has all of the things that we'd expect from a random variable. So over here, I see that I can write down the distribution of X bar. I see that it comes up either 0 or 1. Those are the two possible outcomes. These outcomes are equally likely. I see a 0 one time, a 1 one time, so it comes up 0 half the time and 1 half the time. I notice that my probability sum to 1, so things look good for this to be a probability distribution. I can compute the expected value of X bar. Zero times a half is 0, 1 times a half is 1/2. The expected value of X bar, or mu X bar, is 1/2. And I could work on computing the variance and standard deviation of X bar. What's X bar squared? Well, 0 squared is 0, 1 squared is 1. X bar squared probability of X bar is 0 times 1/2 is 0, 1 times a half is 1/2. Expected value of X bar squared is 1/2. The variance of X bar is expected value of X bar squared, or 1/2, minus the square of its mean, minus 1/2 squared. That's 1/2 minus a quarter, or 1/4. And sigma X bar is 1/2. So for n equals 1, I see that I have this probability distribution. X bar comes up 0, 1, equally likely, has a mean of 1/2, and a standard deviation, sigma X bar, of 1/2. What about for n equals 2? Let's see how things change. Well, our outcomes, we want to construct equally likely outcomes for the sequence of 2 coin flips. So I could get heads, 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 tails, tails, heads, tails, tails. the total number of heads is 2, 1, 1, or 0. And X bar, the average number of heads per flip, per 2 flips, is 1, 1/2, or 0. Just like above, these are equally likely. And just like above, X bar is a random variable. We come down below here. But now X bar can come up as 0, 1/2, or 1. So I need to account for all of those possibilities. And I see that it comes up 0 one time out of 4. Comes up 1 one time out of 4. And 1/2 2 times out of 4, right? That is 2/4. Again, I see my probability is added to 1. That seems good. We can compute our expected value. 0 times 1/4 is 0. 1/2 times 2/4 is 1/4. 1 times 1/4 is 1/4. Expected value of X bar, or mu X bar, is 1/4 plus 1/4, 1/2. We can compute our variance and standard deviation. X bar squared, 0 squared is 0, 1 squared is 1, 1/2 squared is 1/4. X bar squared times probability of X bar is 0 times 1/4 is 0. 1/4 times 2/4, well, that would be, well, 2/4 is 1/2, so that would be 1/8. And then 1 times 1/4 would be 2/8. So my expected value of X bar squared is 3/8. My variance of X bar is 3/8 minus 1/2 squared minus 1/4, or 2/8. 3/8 minus 2/8 is 1/8. And sigma X bar, the square root of that is 1/2√2. So 8 is 2 times 4. So one of the 4's comes out of the radical as a 2, and the other factor of 2 stays inside the radical. So that's what the distribution for the average of 2 coin flips looks like. Its mean and its standard deviation. Let's do 3 coin flips and then combine things together. All right, so for 3 flips, well, one thing that we might see is that, like, for 1 flip, I have heads, tails. For 2 flips, what I do is I just make 2 copies of heads, tails. In front of the first copy, I put a heads, and in front of the second copy, I put a tails. For 3 flips, I can make 2 copies of the 2 flips, and then put another head in front of one of the copies and a tail in front of the other. So there's 1 copy. Oh, skipped 1. There's a second copy. And then I'll just stick a head in front of each of these and a tail in front of each of these. That will get me all of my 8 outcomes, my 2 cubed, or 8 outcomes. These are all equally likely. Let's count the number of heads. 3, 2, 2, 1, 2, 1, 1, 0. And then the average number of heads per 3 flips, 3/3 is 1, 2/3, 2/3, and 1/3, 2/3, 1/3, 1/3, and 0. I have 4 different possibilities for X bar. 0, 1/3, 2/3, or 1. 0 comes up one time out of 8, all equally likely. 1/8 probability for that one. 1 comes up one time out of 8, all equally likely. So 1/8 probability getting a 1 for X bar. 1/3 and 2/3 both come up 3 times out of 8. If I add my probabilities, I get 8 out of 8 or 1. So I think I've gotten everything. And we can go through the same process. I am going through this a bit quickly, I know, but we're kind of doing the same thing a few times here, and this is all stuff that we've seen before. So if you're not catching the details, you should be able to fill them in later without a problem. Getting our expected value, 0 times 1/8 is 0. 1/3 times 3/8 is 1/8. 2/3 times 3/8 is 2/8. 1 times 1/8 is 1/8. Expected value of X bar or mu X bar is 2, 3, 4/8 or 1/2. And on to computer variance and standard deviation. 0 squared is 0. 1/3 squared is 1/9. 2/3 squared is 4/9. And 1 squared is 1. X bar squared multiplied by its probability. So multiplying these two columns, 0 times 1/8 is 0. 1/9 times 3/8, one of the factors of 3 divides out. I'm left with 1 over 8 times 3, or 1 over 24. 4/9 times 3/8, again, one of the factors of 3 divides out. I'm left with 4 over 24. And 1 times 1/8 is just 1/8, or that is 3 over 24. So my expected value of X bar squared is 8 over 24. Or what is 8 over 24? That is 1/3. What do I get for my variance? Sigma squared X bar is 1/3 minus the square of the expected value minus 1/4. That is 1/12. Anytime you have like 1 over n minus 1 over n plus 1, that ends up being 1 over n times n plus 1. And sigma X bar is 1 over root 12, or that's 1 over root 3 times root 4, 1 over 2 root 3. Okay, so let's recap. So let's consider X being the number of heads on one flip. X has a distribution that's 50-50, 0 or 1. Expected value of X or mu is 1/2. And the standard deviation of X or just sigma is it was 1/2 as well, right? Yeah, 1/2. And then let's look at X bar. The average number of heads on n flips. When n is 1, 2, or 3. The distribution when n is 1 X bar 0, 1 equally likely. The distribution when n is 2, it comes up 0 a quarter of the time, 1 a quarter of the time, and 1 half of the time. So this middle value, 1 half, is twice as likely. And for n equals 3, 0, 1/3, 2/3, or 1 are the different outcomes. They come up proportionally 1 to 3 to 3 to 1. These aren't all scaled the same, obviously, as far as height goes, but what is our mean? Mu x bar for n equals 1 is a half. For n equals 2 is also a half. And for n equals 3 is 1 half. And we see that that's just the same as mu x, or we'll just call it mu. From up above here. The underlying distribution that's giving rise to this x bar distribution. And that kind of makes sense. If we like mu up here is already an average. If we kind of like average an average, we would expect to get the average back. So that makes sense. But we do see something really interesting with the standard deviation. We don't just get the same standard deviation. For n equals 1, I get sigma x bar is 1 half. Then I get 1 over 2 root 2. Then I get 1 over 2 root 3. One over 2 root 2, I could write that as 1 half times 1 over root 2. And 1 over 2 root 3, I could write as 1 half times 1 over root 3. Or the standard deviation of the original distribution, sigma, was 1 half. So this is like sigma over root 2, and sigma over root 3. And I could really write this as sigma over root 1, I suppose, if I really wanted to. So what do we see? That as we start averaging together more flips of the coin, of the fair coin, our distribution goes from being uniform, from being flat, to being something like peaked in the middle, symmetric, tailing off to both sides. Hey, that sounds a little bit like a normal distribution. Our mean, the mean of x bar, mu x bar, stays the same as the original mean for the population, or for the original underlying distribution, mu. But our standard deviation does not stay the same as the original underlying standard deviation. It gets divided by square root of 1 when n is 1, square root of 2 when n is 2, square root of 3 when n is 3. It gets divided by what looks like square root of n. Now, why did we go through this? Well, this leads us into the central limit theorem. I want to be very clear. This is not a proof of the central limit theorem. This is kind of a demonstration of some of the concepts of the central limit theorem in a special case. A full proof of the central limit theorem is well beyond the scope of this course, so we won't be proving this. Bump this up to the correct line. So we won't be proving the central limit theorem, but we'll be stating it. We've given, a bit of evidence that it might be true. And I hope that in the near future, well, particularly in the testing for normality, I hope we'll give a little more evidence that the central limit theorem, um, seems to be true. So anytime that we give a theorem, I intend to either prove it carefully, which we did for a couple of our previous theorems, or I intend to at least give you some empirical evidence, some simulations and so on that suggest that it's true. And depending on how much time we have, we'll either go through that empirical evidence today, or we might punt that to the supplemental video as well. Oh no, I actually did want this on the next line. So what does the central limit theorem say? The first thing it says is for large n. Remember, with the law of large numbers, we also had this for large n caveat. The central limit theorem is true in the limit as the sample size goes to infinity. It's practically approximately true for large enough sample size. What does it mean that a sample size is large enough? Well, that is a tough question to answer. We'll see in a little bit what one take on that is anyway. For large n, the sampling distribution of the sample mean, or what we mean by that is we think of x bar being the mean of a given sample. That x bar is a random variable, just like it was up here. That x bar has a probability distribution. It has its own mean, mu x bar, and it has its own standard deviation, sigma x bar. So for large n, the sampling distribution of the sample mean, or in other words, the distribution of x bar, taken with replacement from a population, here the underlying population has mean mu x, or maybe just mu, and standard deviation sigma x, or maybe just sigma, is three things. One, it's approximately normal. In the limit, it becomes normal. So this pattern that we saw where we said, hey, this starts looking a bit like a bell curve, that actually is a valid pattern. It wasn't just deceiving us, and if we got up to n equals 10, it would look like something different or be bimodal or something. No, it actually is heading towards a normal distribution for larger and larger sample sizes. That normal distribution has two parameters, mean and standard deviation. Its mean, mu x bar, will be the same as the original mean from the original population. Its standard deviation, sigma x bar, will be related to the standard deviation of the underlying population, but it's going to be sigma x over root n. That's the same pattern that we saw up here. Again, we recognize the pattern. That wasn't a guarantee that pattern would carry on forever. We also made an argument previously for why this should be true. That was part of that whole Chebyshev and law of large numbers discussion. So for large n, the sampling distribution is approximately normal. The mean is the same as the mean for the underlying population, and the standard deviation gets divided by root n. So these two aren't super surprising because, again, we kind of saw them back in like chapter 5 or so, but really the big interesting idea is this one here. So a couple notes on this. Again, what is meant by large n? How big of a sample size do I need so that I can apply the conclusion of this theorem confidently? Well, a rule of thumb, what's a rule of thumb? It means, this is something that it's not mathematically provable, but it's something that, in most practical applications, most of the time, historically works well. So that's what a rule of thumb is, or a heuristic. It's something that works well most of the time for most applications, right? Different applications have different degrees of accuracy and precision that are needed. There are different amounts of impact for making a wrong decision, right? I mean, some fields have, life or death decisions, like you don't want the person building your bridge or building your elevator safety systems to be, to be using the same heuristics as somebody who's, manufacturing a billiard table or something like that. If you're a little bit off on one of them versus the other one, the consequences are much different. So, but anyway, the rule of thumb is that n bigger than or equal to 30, if we have a sample size of at least 30, for most applications, most of the time, that's good enough for us to apply the conclusion that the distribution of the sample mean is approximately normal with this mean and standard deviation. And it turns out that if we know that the underlying population is normally distributed, so like up here, we started with an underlying population, so to speak, that was uniform, not normal, right? It was flat, not normal. But if we had started with, instead of a uniform distribution, if we started with a normal distribution for the underlying population, then it doesn't matter. Then actually the result of our central limit theorem applies exactly. It's not approximately normal, it's exactly normal with this mean and standard deviation. If we start with some other distribution, as long as we have sample size at least 30, the rule of thumb is we can apply this conclusion. There are some huge caveats here, particularly if we have high levels of skewedness. So one example we might look at is, say, a Powerball example where we have a lottery where most of the prizes, the vast majority of the time, you're going to either lose money or maybe win a little bit of money, but occasionally you win an enormous amount of money. That's incredibly highly right skewed. What is your sample size going to have to be to make the average, say, win per ticket look normal? It's going to have to be enormous. An n of a million or something, or 10 million doesn't do it, not even close. So in very strange situations, this rule of thumb doesn't really apply, but in most usual, somewhat normal situations, it's good enough. And that is the rule that we will take for this course. So if we have a sample size of at least 30, we can use the central limit theorem as far as this course is concerned. Outside of this course, there might be other caveats that we might or might not want to use that rule of thumb. The huge thing about the central limit theorem, the thing that almost makes it magic, I mean, it makes sense that if we start with a normally distributed population, we compute the mean and we end up with the normal distribution for X bar. Like that kind of makes sense. But the thing that really is interesting is we've said nothing about the original distribution up here. I didn't say for large N and for a sample coming from a normal distribution, this is true, or for a sample coming from a symmetric distribution, this is true, or for a sample coming from a uniform distribution, this is true. And I just said for large N, the sampling distribution of the sample mean, blah, blah, blah. We have really no constraints placed on the original distribution other than it has a mean and a standard deviation. That might not seem like much of a constraint at all. There are distributions that have like infinite standard deviation, so those are excluded here by saying that we have a standard deviation sigma x, implying that we have a standard deviation that's a real number. But if our distribution that we write down, whether it's a uniform distribution or an exponential distribution or a normal distribution, whatever it may be, the central limit theorem will apply to it. And really interestingly, if I start with a uniform distribution and I start taking averages, the averages tend toward, or what? If I start with a uniform distribution, the averages tend toward a normal. If I started with an exponential distribution, it looks kind of like this. The averages would tend toward a normal. If I started with, I don't know, some, crazy bimodal distribution, the averages would tend toward a normal distribution. That's kind of the magic of this central limit theorem. There's something really special about the normal distribution. or at least this family of normals. Because in some sense, like every distribution, well, everyone with real number mean and standard deviation anyway, when we take averages, they tend to a normal distribution. It's not just if we start with a normal, we tend to a normal. We'd expect that, but if we start with essentially any distribution, we tend to a normal when we take averages. So why is the normal distribution so special? Well, it has two important characteristics. One is that it has this stability, this sense that if I add together or average together two normal distributions, I get exactly a normal out. That's really important. That's why we were able to say or normal population here. Even if I only have a sample size of 2, if I have a normal population, then the result of the central limit theorem holds exactly. So if I average together 2 draws from a normal distribution, I get exactly a normal out. So averages of normals are exactly normal. So it has this like stability property, right? Averages of, say, uniforms are not uniform, right? I did not get a uniform distribution over here when I averaged uniform together. I got something that looked a bit like a normal distribution. So the normal itself is stable. If I have an underlying population that's normal and I start averaging draws together, it stays exactly normal. That's a property of the normal distribution. The really interesting thing is that it's actually the only distribution that has this property, and it also has finite variance. One of our assumptions was that we had a finite standard deviation or variance. So as long as our underlying population has a finite variance, it's got to end up going to this attractor, this normal distribution. So that's kind of the magic. There's a really deep way to prove this, to really not necessarily even prove it. There are a lot of ways to prove the central limit theorem, but to really get a deep understanding of why this is true. So there's this idea of stability. And it turns out that kind of roughly speaking, for this class of distributions that are alpha stable distributions, there's a parameter. The parameter is often just written as alpha. And for a distribution to be stable, I think I have this the right direction. I might have this the opposite direction. I have to think about it. But for the distribution to be stable, it's alpha has to be greater than or equal to 2 for this random parameter. And for it to have finite variance, alpha has to be less than or equal to 2. So to have a stable distribution with this kind of a property, with finite variance, the only overlap is exactly at alpha equals 2. And alpha equals 2 is exactly the family of normal distributions. That's the exact class of distributions that sits right there exactly at alpha equals 2. So it's really an elegant mathematical proof, and there's really some deep mathematics and statistics underlying the central limit theorem, and not just the proof of it, but really understanding why it's true. It's one thing to prove that something's true and follow a set of steps and say, okay, I'm convinced that this is true, but it seems so strange that any distribution effectively with finite variance, you start averaging together draws from it, and it tends to a normal, no matter what distribution you start with. And this is really the deep reason why. It comes down to this stability and that kind of overlapping of those two intervals exactly at alpha equals 2, which is exactly the normal distribution family. So there's really a lot of deep mathematics here, and central limit theorem is probably one of my favorite theorems. I think you're officially a nerd if you have a favorite theorem. So I have a couple of favorite theorems. The other kind of less mathy way that I like to think about the central limit theorem, the normal distribution, is it's a little bit like as we start taking larger and larger samples from a population, it's a little bit like we had, say, a billiard table and we're bouncing a billiard ball around on it kind of randomly. And if I, bounce this way or that way or whatever, it just keeps bouncing around. But if the billiard ball falls into a pocket, it falls into the pocket and doesn't get back out. And it's maybe a little bit very, morally speaking, like that. That is, we're kind of like working our way around this, space of probability distributions. Maybe we run a little bit this way or run a little bit that way, but eventually we kind of get sucked into the normal distribution. And once we're in the normal distribution, because it's an attractor, we can never get out. So once something starts behaving like a normal distribution, it basically successive averages behave like a normal distribution from that point forward. That's a much less accurate description of why it should be the normal distribution, but maybe a little easier to understand. It's like we're jostling around this billiard table with all of these balls on it, and they're eventually all going to fall into pockets. Some of them might take quite a while before it falls into the pocket. In some cases, we might need a really large N for this conclusion to be approximately true, but it'll eventually happen. I've already mentioned that if the population is normal, the central limit theorem holds for all N. We would have exactly normal distribution with this mean of standard deviation, not just approximately. And some folks actually call the central limit theorem the fundamental theorem of statistics, and kind of each big branch of math gets its own fundamental theorem. Sometimes it's a little more official than other times. So there's the fundamental theorem of calculus, this thing that kind of connects two seemingly very disconnected ideas in calculus, differentiation and integration. There's the fundamental theorem of algebra that says for a polynomial, how many roots do you have, right? For an nth degree polynomial, you have exactly n roots in the complex plane. So there are all these fundamental theorem of blank for different math fields. And a lot of people argue that the central limit theorem is essentially the fundamental theorem of statistics. And we might call something like the law of large numbers, maybe the fundamental theorem of probability, something like that. I think maybe I've heard people call it that before. These are less official than those other ones. But when we move into chapter 7 and 8, confidence intervals and hypothesis tests, where we're really trying to take the mathematical models that we've developed in chapters 4, 5, and 6 and kind of marry them to the chapters 2 and 3 ideas of the real world data. We're trying to smush those two together and come up with something that allows us to make inferences, allows us to take data from the real world, apply mathematical modeling to it, and make guesses about what we think will happen in the real world, and hopefully most of the time be fairly accurate in our guesses. This is really, the central limit theorem is really the driving force behind that marriage of the actual data with the mathematical models. It's really the basis of all of our discussions in chapters 7 and 8. One of my undergrad professors, Mark Maxwell, super fun guy, so he was hilarious, had a lot more charisma than I have. But he did his PhD in statistics, so a lot of places have a math department and a statistics department that are separate. We kind of have everything bundled together at CCAC, and some places have that model as well. But basically, he said one time, he was like, yeah, if you want to get a PhD in statistics, what you'll end up doing is just some variant of the central limit theorem. You'll prove some variation of the central limit theorem. That's essentially how important it is. If you're doing any series, I mean, it's obviously it's a bit of hyperbole, but if you're doing serious research into anything in statistics, you're going to run into the central limit theorem in some form at some point. Okay, so that is the central limit theorem. The sampling distribution of the sample mean, the distribution of X bar for a sufficiently large sample size is approximately normal, with mean the same as the underlying population's mean as standard deviation sigma x over root n. The other very important thing is, that I don't think I mentioned explicitly, is the larger the sample size, the lower the standard error in the mean, the lower the standard deviation of the distribution of X bar. So if I take a very large sample, this standard deviation is very small. My distribution of X bar, essentially all of my mass or probability of my distribution is concentrated at the mean of the underlying distribution. In other words, if I take a really large sample, my guess at what the population mean is based on the sample mean is going to be very, very accurate. It's going to be very, very close to the sample to the true population mean, right? This is the distribution of X bar, my sample means, and it's like almost always really close to the actual underlying population mean. That's where this marriage comes in chapters 7 and 8, where we're connecting sample ideas to population ideas. Okay, so we have the central limit theorem for the mean. Now, we saw before in our discussion of the law of large numbers that we kind of had a weak law of large numbers that said that, the mean goes to the mean, the sample mean goes to the population mean. That was nice. But it seemed to fall a bit short of the actual law of large numbers, where we said the frequency distribution that you get from a big sample kind of looks like the frequency distribution of the population. But we weren't able to connect those two. We're going to do a similar thing here. And that's, I think, one of the valuable points of going through that previously is we're going to see how we can take this statement about the mean and convert it to a similar statement, a central limit theorem for a proportion, for a probability of an event. So your book, I think, actually starts with the central limit theorem for p hat, which I think is a bit silly because, number one, we mostly want to use it for the mean in chapter 7 and 8. We do talk about p hat, but I think the mean is more important. And also the mean is just easier to understand. It's less abstract. But let's take a look at the central limit theorem for p hat, the probability of an event, this binomial probability. So suppose we're interested in P, the probability of an event, or what we might call just probability of success, thinking back to the binomial distribution section. And we estimate this by P hat, or the sample probability of success, number of successes over number of trials. Suppose we have data from n trials. We have n outcomes, y1 through yn, and each of these yi's are either in the event, they're either a success, they satisfy the event, or they're not in the event. If we let xi be, say, 0, if we don't satisfy the event for one of our y's, and if we do satisfy the event for that y, we call it xi1. And we've discussed this before. We talked about this in the proof of the weak law of large numbers. So go back to that discussion for the details. But we said that the expected value of x, mu x, ends up just being p. So why is that? Well, we're just adding up. We're just looking at the average number of successes per n trials. So that's just np divided by n is just p. And sigma x for a single trial is square root of p times 1 minus p. Again, we've worked through this before as well. So p hat is the sum of the xi's over n. It's the sample probability of the event. But I know that the sum of the xi's over n is just x bar. Okay, so what can I say then? By the central limit theorem for large n, the sampling distribution of the mean, or in other words, the sampling distribution of p hat, is approximately normal with mean that's the same as the underlying distribution, with mean p, and with standard deviation, the underlying standard deviation divided by root n. or, right, sigma x over root n is root p 1 minus p over root n. But here I have parentheses, exponents, roots, multiplication, division, addition, subtraction. I have a distributive law that can distribute multiplication, division over addition and subtraction, but I also have a distributive law where I can distribute exponents or roots over multiplication or division. It's right distributive. So I can, in a sense, factor out the root, the 1/2 power, to make this root p1 minus p over n. So that's where this comes from. Right. So the sampling distribution of the mean, which in this context is just p hat, the sampling distribution of p hat is approximately normal, with mean the same as the underlying population, just p, and standard deviation sigma x over root n, or that's just this whole root p1 minus p over n. So that's where that bit comes from. And the rule of thumb here is a little different. Up here, the rule of thumb for an actual mean x bar was the sample size at least 30 or normal population. And down here, we say that n is sufficiently large if n times p is bigger than or equal to 5 and n times 1 minus p is bigger than or equal to 5. Or in other words, if the expected number of successes is at least 5 and the expected number of failures is at least 5. So for this kind of proportion or probability of an event situation, we can apply our central limit theorem by the rule of thumb if we expect to have at least 5 successes, at least 5 outcomes in the event, and at least 5 failures, at least 5 outcomes not in the event. Okay. I think I want to take a minute here and just work through a couple Excel files. So let me stop my share for just a second to get my screens sorted out a bit here. Okay, I'm going to post an Excel file into chat. Okay. And that's what we'll be working with in just a second here. So since we are doing okay on time, I want to go through the empirical evidence for central limit theorem. Are there any questions up to this point? Okay. Right, so this is the Excel file I popped in the chat. And basically what we're going to do is we're going to look at some different scenarios and show that that this seems to be true. Again, this is giving some empirical evidence, but I hope it's at least somewhat convincing. So like I said, we don't really have the mathematical background or frankly the time in the course to prove the central limit theorem fully or carefully, but we're going to give some evidence that it is true, I think. And we're going to use simulations to do that. We'll also see some more simulations and some more evidence when we come to the confidence interval section. So that'll, bolster this a little bit more, hopefully at that point. Okay, so this first page here, the one that says coin toss 10 at the bottom. Here what I have is a sequence of trials. And you see each of these has this equals random between 0 and 1. So this is choosing a random number either 0 or 1. It's a coin flip, basically. The 0 meaning we got 0 heads on that flip, so a tails, and 1 meaning we got 1 head on that flip or we got a head. We have 10 flips, and we can look at the sum of the flips. This is a little bit different than what I have over here for the mean, but we could also apply the central limit theorem to the sum. I mean, the sum is just n times the mean, right? So it's basically the same. So we could rephrase this in terms of the mean if we wanted. I just left it in terms of the sum here so we can see a different perspective on the central limit theorem. And I have repeated this with 100 trials. So we've done 100 times, we've done 10 flips of a coin. And this is random. You can hit, is it F9? Yeah, F9 will recalculate it. Oh, let me try to move this out of the way. There we go. And over here, I have a table where I just have the frequency distribution. Now, the really big claim in the central limit theorem, these claims we've shown before. We've shown that averages, that means of averages, the mean stays the same as standard deviation of averages. We get this 1 over root n bit out of there. We showed that back in chapter 5. So that's not the super surprising part. We might have forgot about that, but you know, if you want, you know, the argument in favor of this part, just look back at the proof of the law of large numbers. But this is really the interesting thing, approximately normal. Okay, so with a coin toss, we showed that, you know, for n equals 1, 2, or 3 coin tosses, things seem to start moving towards a situation where we have a peak in the middle, some symmetry tailing off to the sides. But this was kind of in a perfect world. What if I have samples of size 10? Do these samples, do their distribution of the sample means, or the sample sums, actually look normal? And here I have 100 samples, each of which is size 10. So by the way, this is only n equals 10, not n equals 30. But it turns out this is a nice, well enough behaved system that even with a sample of size 10, we get pretty good results. You can hit F9 and it will randomly recalculate. So this one doesn't look quite as good as the last one. But these all look more or less like they're peaked in the middle, roughly symmetric, and tailing off to the sides. Some of them don't, you know, the peak isn't as nice as we might get in other ones, but you know, that's how randomness works. If we look at only 5 coin tosses, and again, the sum. So here I'm averaging together or adding up 5 coin tosses. And again, doing that 100 times. I see that I start to get, I mean, if I really blur my eyes and I really, you know, want to make the argument, maybe I could argue for a bit of symmetry, peak in the middle, tailing off to the sides, but it would be kind of, you know, it seems like maybe about half of them I could make, like this one might be a nice one. I could, you know, screen cap this one and show you this one, and you'd say, oh yeah, I buy that. But you know, then we might get one like this, and you'd say, wait, I don't know if that really looks like a normal distribution, or right, something like this. I don't know if that looks like a normal distribution. It almost looks left skewed. So if we're only at an n of 5, even for a nice simple, you know, cooperative, so to speak, system like a coin toss, where we don't have a lot of skewedness to start with or anything, it doesn't seem like this approximate normality really holds. I'd have to really, you know, cherry pick my evidence to make a good argument. But even with an n of 10, it seems much more often that I get a distribution that looks roughly normal. And if I come over here to 30 coin tosses, depending on how I kind of cut my data, I cut my histogram up, you know, I'm almost always now getting something that has a pretty clear peak in the middle and tails off rapidly to both sides. And now again, this is still only with 100 individual sample sequences. If I went up to 1,000 or something like that, it would be even better, but Excel tends to get pretty laggy pretty quickly on some of these calculations. Okay, just to show another example, we have here a die roll. So here, each of these is choosing a random number between 1 and 6, so essentially a die roll. So I have 10 die rolls. I got, rolled a die 10 times. I got a 2, a 2, a 4, a 5, etc. That was trial number 1. And here I am computing the average instead of the sum. Like I said, just two different perspectives on the central limit theorem. You could reframe all of this in terms of, the sampling distribution of the sum, the sample sum, taken with replacement would be, well, here you would have to have n times mu x, and here you'd have to have root n times sigma x, but it would be a very similar type of result. And I can see that I have a frequency distribution over here for the averages. And here's what the distribution of averages looks like. And this is for an n of 10. You see, it looks pretty good. I think that would convince me that it's approximately normal. If I look at an n of 5, only 5 die rolls that I'm averaging together. Again, it looks a little more questionable, right? Sometimes I might be convinced that it's approximately normal. Other times I might be, questioning it. So sometimes it doesn't, this almost looks more like uniform and then drops off. So with an n of 5, it starts to seemingly break down, even for a pretty nice, starting with a uniform distribution, nice 1 through 6 equally likely. For 30 rolls of a die, I mean, if I look at this histogram on the left here, that's not very informative because almost all of the data ends up just in these middle 4 boxes, these middle 4 bins. That's not super helpful. So if I go a little bit finer, break down those middle bins, instead of jumping by half a unit, if I jump by a quarter of a unit, I get a little better resolution. And for an n of 30, I'd probably be pretty confident that this looks normal. This looks like a normal distribution. Peaking in the middle, that's actually a particularly bad one, but peaking in the middle, roughly symmetric, tailing off to the sides. Now, if we look at the Powerball, this was one of the supplemental problems in chapter 5, just to kind of work through for practice. We see that if our jackpot was 0, our expected win per ticket is negative 64 cents, and the standard deviation of wins is about $440. That's mainly coming from the $1 million prize, right? This 194,000 is essentially the entire expected value of W squared. It's essentially the entire variance in standard deviation. With a jackpot of 120 million, though, my expected win is 4.5 cents per ticket. My standard deviation of wins goes way up to $9,000 now, though. But importantly, this is a tremendously skewed distribution. I have like something like a 1 in a billion chance or something of winning like $120 million. So for this one, I did basically the same as this, right? Where I took, say, maybe an n of 5 or 10 or 30, say draws from a Powerball, average it together. That gave me one average, and then I did that a bunch of times to get a bunch of different averages. But here, instead of using an n of 5 or an n of 10 or an n of 30, I used an n of 10 to the 5th of 10,000 or 100,000. My frequency distribution is that I essentially almost always end up with an average of negative 0.87 to 0.89. Remember, I'm expecting an average of positive 0.04. So what does negative 0.89 come from? Well, that comes from if I were to not win the Powerball and not win the $1 million, right? And I guess probably also not win the $1,000 or so. Like that's, basically I didn't win any of the big prizes. In 10,000 draws, if I don't win any of the big prizes, that's these numbers. If I win one big prize, maybe I win the $1 million or something. That happened a few times. But if I look at my distribution, here's from negative 0.89 to negative 0.78. Remember, my mean is supposedly 0.04. 0.04 is going to be way off to the right. It's going to be like two houses down the block off to the right. That's what my distribution is supposed to be symmetric about. That's clearly not the case. Even with an n of 10,000, I keep saying 10,000, 100,000. Uh, yeah, right. Yeah, 100,000. Um, so yeah, even with an n of 10, even with an n of 100,000, I keep wanting to say 10,000, and now then I was questioning myself. Even with an n of 100,000, getting 100,000 tickets, we're still nowhere near having an approximately normal distribution that's centered around the mean. And even if we go up to 10 million, and by the way, I did these on MATLAB, a programming language, because Excel obviously would not be able to handle this much data. So here I just let this run overnight one night, and by morning it had done 32 draws of this, and I just stopped there. So with 32 draws, we can see that we're still basically nowhere near around this, what was it, positive 0.04. So we should be like somewhere between this negative 0.1 and positive 0.1 is where we'd expect the center of our distribution to be. We see almost all of our data down here to the left. And then a couple of times that we happen to win the Powerball. This is for 10 to the 7th draws. So that would be a million draws, 10 million draws. I cannot get my powers right today. That would be 10 million draws for each of these. So in this 10 million tickets, we won the Powerball once, and that's what bumped us all the way over here to the right. And in all of these other 10 million draws, these other 31 or so of those 10 million draws, we didn't win the Powerball at all, and we ended up nowhere near positive 0.04. So this is a case where n equals 10 million, certainly bigger than 30, is not enough for us to even get close to something that's approximately normal, centered at the mean. This does not look like a normal distribution centered at 0.04. Still very skewed to the right. And the center is nowhere near this 0.04. So, so that's an important caveat, I think. If we, have a really crazy distribution like the Powerball distribution, or, where does this come up a little more practically? Things like life insurance, right? From the standpoint of an insurance company, when they look at your policy, they say, all right, like almost certainly I'm not going to have to pay out a bunch of money and I get my small premium, but there's some really little chance I'll have to pay out a whole bunch of money. A life insurance policy is basically like the opposite of a Powerball, right? The insurance company is taking in a little bit of money, and they might, very rarely, but they might have to pay out a ton of money on that. So things like pricing life insurance can be quite challenging because, well, I mean, maybe a life insurance company has 10 million policies, but we see that for something like this, even an N of 10 million isn't enough that we can really apply a lot of nice statistics coming from maybe the central limit theorem. Okay, so hopefully that gives a little bit of empirical evidence uh, for the central limit theorem. Let me switch my screens back over. And then we'll start a last problem on calculations involving the central limit theorem. Sorry for all of the juggling of windows today. I think this is the most windows that I need to juggle in any given class period. Okay, so let's take a look at this example. Oh. So take a look at SAT scores. Let's assume the national average SAT score, say math plus verbal. I don't know why they keep changing how they calculate it, but we'll just do math plus verbal, is 1,028. And the population standard deviation is known to be 100. If we assume scores are normal, let's compute the probability that X, a randomly chosen student score, is bigger than 1050. So this is not a central limit theorem problem. It's just a basic normal distribution problem as kind of a warm-up. We know this should be less than 50%. One standard deviation above 1028 is 1128, so it should be a little less than 50%, but not like 2% or something. Let me make this a question in Z. So it's going to be the Z score for 1050 is 1050 minus 1028 over the standard deviation of 100, or that's 0.22. 50 minus 28 is 22, divided by 100 is 0.22. And I see that I can use symmetry. I could use complementary events here as well if you prefer that, but I can use symmetry. I have a right tail area. I need a left tail area. My positive 0.22 flips to a negative 0.22, and my right tail area to a left tail area. This is Z. So this is probability Z less than negative 0.22. And I closed too many windows. Get my normal distribution up again. There we go. And so we were looking for the area to the left of a negative Z score. Here's negative 0.2012. So that should be 0.4129. So 41.29% chance that a single randomly chosen student scores above 1050 on the SAT. Now let's look at this question here. What's the probability that the average score of 30 students, maybe an average score of 30 students in someone's class, is above 1050? In other words, what's the probability that X bar is above 1050 for a sample of size 30? This might, initially seem like the same question, but remember that the distribution of the mean, well, that distribution has the same mean, but it has a different standard deviation. And that's going to actually have a big impact on this answer. So here we know that X bar by the central limit theorem is approximately normal. And bigger than or equal to 30, we can conclude that it's approximately normal. With a mean that's the same as the underlying population's mean, 1028. So that kind of center point doesn't really change, but the standard deviation changes a lot. Sigma X bar is sigma X over root N, or that is 100 over root 30. So what is 100 over square root of 30? Well, that's about 18.3, let's say. So now in my distribution x bar, still centered at 1028. So 1050 is still off to the right. I didn't quite leave myself enough room. So I want probability x bar bigger than 1050. And again, I switched that to a question in Z, going through this a little quickly, because it's pretty similar to what we just did. But what's my Z-score? It's not going to be 0.22 anymore. It's going to be 1050 minus 1028. The numerator is the same, but over, well, over 100 over root 30 or over 18.3. So my Z-score is going to be 22 over 18.3. It's actually going to be 1.2. 1.20 approximately. Or this is the probability that Z is less than negative 1.20. Or that's about 11.51%. So what changes is this standard deviation down here. That standard deviation gets smaller. That pushes my Z-score further away from the mean. And since my 1050 being bigger than 1050 does not cover the mean 1028, we're getting pushed further into the tail. It's getting less likely. About a quarter as likely as it was before. Try the same calculation with a sample size of 200. We'll do that when we come back and continue on with this section, finish up chapter 6 and start chapter 7 next time.